Okay, it looks like you restarted the stream. Are we ready
Yes,
to
you're ready to go.
Great. So yeah, well, we're starting a session on formal analysis. This session is about quality over quantity. We got two excellent talks ready for you. As usual, ask your questions here on Zoom chat or in Zulip. And if you ask in Zulip, maybe prefix your question with the target of your question. But the first talk will be systemization of knowledge on computer-aided cryptography, and Kevin Liao will be giving the talk. Go ahead, Kevin.
Awesome, thanks for the introduction. So today I'll be telling you about how we can use computer-aided tools to develop cryptography. And this talk is based on a systematization knowledge paper, which was written with the many wonderful co-authors listed here. So I think we're all familiar with how difficult it is to get cryptography right. Widely deployed protocols often have high-profile design flaws, heavily scrutinized libraries regularly have bugs, and otherwise secure and correct code can still leak secrets through side channels. So clearly, the current way we do cryptography just isn't delivering the high level of assurance that we expect. And this brings us to computer-aided cryptography, which is an active area of research that aims to address these challenges. But what exactly do we mean by computer-aided? You know, we've long used computers to develop cryptography. So by computer-aided, we're referring to formal machine checkable approaches to help in the design, analysis, and implementation of cryptography. And one of the main goals of computer-aided crypto is to improve security without sacrificing the things we care about, such as interoperability and performance. And so how exactly can computer-aided crypto help? Well, there are a variety of tools that address different parts of the problem space. We've broken it down to the following three layers: design level security, functional correctness, and implementation level security. So for design level security, today security analysis is primarily done on pen and paper, which is highly error prone and makes double checking security analyses extremely tedious. With computer aided tools, we can formally specify designs and automatically check that they enjoy important invariants or otherwise discover new attacks. So using TLS as an example, before version 1.3, the protocol's design phases didn't involve computer-aided analysis, and the process was highly reactive, leading to an endless cycle of attacks and patches. And given the complexity of the protocol, early analyses considered only highly simplified cryptographic cores, but once the academic community started considering more detailed aspects of the protocol, many new attacks were discovered. And this dynamic really changed during the proactive design process of TLS 1.3. The academic community provided analysis throughout developing multiple drafts. And in studies using symbolic analysis tools such as ProVerif and Tamarin, the process of verifying TLS and actually even just formally specifying it revealed flaws, led to protocol improvements, and otherwise clarified the documentation of security guarantees. For correctness, today's solutions for avoiding implementation bugs include code testing and auditing, but unfortunately, code testing is incomplete and is pretty unlikely to catch the kinds of correctness issues we deal with today. But with computer-aided tools, we can formally verify that code is free from memory errors and that it behaves according to some design specification on all possible inputs. For example, OpenSSL has had a long history of bugs, which probably isn't surprising given the demand for highly optimized code. For performance, developers are required to multiplex implementations by hand for each combination of algorithm, parameter choices, and hardware platform, which increases the risk of introducing bugs. Fortunately, things are starting to look different today. For example, recent work from the Project Everest team on HackleM presents a new methodology in which developers can write generic code in a verification-friendly language, check that it enjoys properties such as memory safety, correctness, and constant time, and then compile the code down to different platforms that support vector instructions. And this significantly reduces the manual effort needed to add new implementations and also minimizes room for error. And then finally, for implementation level security, today, in order to protect against, say, timing side channels, developers need to apply tricky constant time coding recipes and just hope that they haven't missed any vulnerable pieces of the code. And with computer-aided tools, developers can automatically check whether or not their code is constant time. And it turns out that writing constant time code really is pretty unnatural and difficult to do. A botched patch for a timing vulnerability in TLS led to the Lucky 13 timing vulnerability in OpenSSL. And in turn, the Lucky 13 patch led to yet another timing vulnerability. But fortunately, today, there are many tools that let developers annotate program inputs as either public or secret, and then automatically check that the program is constant time. And these have already been applied to many real-world libraries, including OpenSSL. And at this point, I think it's important to emphasize that computer-aided crypto is not just academic crypto. It really is real-world crypto. And I've already touched on TLS 1.3, but AWS's key management service also has machine-checked proof of security. And provably secure and correct code is also being deployed at scale in Firefox, Google's Boring SSL library, and more recently in the Linux kernel. And even though these success stories are great, in order to fully appreciate the benefits of computer-aided crypto, it's also important to acknowledge that formal guarantees do come with limitations, namely that to make formal analysis tractable, formal models are almost always a simplification of the real world. So for design level security, this means that protocol models are often simplified into a cryptographic core that ignores many details about designs and attacker capabilities. For correctness, there may be gaps between what's being verified and the output machine code. For example, verification might be carried out on a verification-friendly representation of the source code rather than on the source code itself. Or if verification is performed on C code, we have to trust mainstream C compilers, which frequently have bugs. And even if the code that they produce is functionally correct, they might introduce side channels that weren't present in the original source code. And for implementation level security, formal models just can't capture all the physically observable effects of hardware, which leaves room for unaccounted side channels. And even further, side channel attacks such as Spectre reveal gaps between what we think is being leaked and what's actually being leaked out in the real world. On top of it all, in order to carry formal guarantees all the way down the stack, we have to make sure that we haven't left any gaps in our modeling between layers. Closing these gaps, though, does leave many exciting future research challenges. This first one is more of a suggestion, but an important lesson we learned from TLS is that standardization processes can embrace design changes that simplify security arguments and help modular reasoning. The TLS 1.3 design incorporated many suggestions from the academic community, from design, security fixes to fixes that simplified automated analysis. To carry guarantees, correctness guarantees down to machine code, they can be established at source code level and then compiled using a verified compiler, such as CompCert. But the problem is that today's verified compilers produce pretty slow code. So important future work is to incorporate more optimizations, including support for, say, SIMD instructions. Alternatively, there's a lot to be gained if we could focus more efforts on scalably verifying assembly code directly, which currently requires quite a bit more work than verifying C code. To achieve a sound formal treatment of protecting against side channel attacks, Guo, Jerome, and Heiser have argued the need for a new security-oriented hardware-software contract. Today's ISAs describe what a developer needs to know to write a functionally correct program, but they're an insufficient specification when it comes to writing secure programs. And so in order to carry side channel countermeasures at the software level down to hardware, we need ISAs that capture, for example, the temporal behavior of programs. And finally, to bridge any gaps between layers, we encourage efforts on consolidating all of these guarantees. So the holy grail of computer-aided crypto would be to deliver guarantees on machine code that match the strength and elegance of guarantees on cryptographic designs. So now that you're all a little bit more familiar with computer-aided crypto, let's think about what computer-aided tools might change in the grand scheme of things. So even though we've made some great strides, I think the answer is that it's not totally clear yet. You know, will computer-aided crypto fulfill its promises and put graphic designers out of work? Well, it's only recently been deployed in the wild, so I think it remains to be seen how well these formal guarantees actually hold up. But it's important to remember that security isn't about being perfect, but rather raising the bar for attackers. So maybe we shouldn't expect a world without high-profile crypto vulnerabilities, but maybe just a few per year instead of like 10 per year. What I do know for sure is that this will be a very exciting research area for many, many years to come. So with that, I hope I piqued your interest in computer-aided cryptography. If you want to learn more, I hope that you'll check out our SOK paper, and I'll be happy to take any of your questions. Thanks.
Thanks for that talk, Kevin. We're starting to get some questions on Zulip. Thanks for that. So the first question I'll ask is from Watson. It's about OpenSSL and specifically X509 verification. Is there any research on formalizing and verifying implementations of X509 verification?
Off the top of my head and from our literature search, not that I'm aware of.
Okay, another question from Paul Grubbs. Do you think it's especially important to use formal methods for crypto, or should all systems be designed and implemented using formal methods?
Yeah, that's a great question. I mean, in an ideal world, we would have formally verified system code and all the way down the stack. But I think for crypto, I think we definitely should. I think crypto is kind of the sweet spot where the volume of crypto code is not as large as, say, like an operating system or a compiler. And so it really is possible to achieve best-in-class performance for the schemes we care about. And so I think even though verification is quite expensive, we're not losing much in terms of things we care about, such as performance. So I think there is a huge motivation to have verified crypto code out there.
Great. Wow, the questions are really pouring in. I'm gonna triage the question according to the number of thumbs up they're getting. So the next question I'll ask is from Frank Davis. I don't know if this is an easy question to answer, but Frank is wondering about the tools available, the current set of tools available, and he's listing some that he's seen, like Cryptol and CPSA. I guess you shouldn't just list all the tools you know, but is there a good place to go to understand all the tools that are out there?
Yeah, so definitely check out the SOK paper. So the SOK paper has a comparative analysis of all the state-of-the-art tools that you would ever hear about. I haven't talked about that much in this talk, but you should definitely check out the SOK paper for those.
Okay, great. How much of, so I assume this is a question from Richard Outerbridge. How much of this entire picture depends on invisible compiler optimizations?
Invisible compiler optimizations.
In terms of gaining assurance, I suppose, about the result of the compiler, relating the compiler's output to the source code.
Right. So I can speak to sort of like two strands of like verification method for this. So obviously, if you want to verify C code, then you either trust the compiler or you use a verified one. And there are verified compilers that do preserve side channel countermeasures. There's recent work from Jill Barth et al. That does this. And so I guess if you don't want to trust the compiler, then you would have to go this route. Alternatively, there's a lot of work now on verifying assembly code directly. And so all of the countermeasures you would want, such as correctness and side channel protections, directly are established on the target level code.
Okay, great. I think we'll maybe do one or two more questions, depending on how long your answer is. A question from Ayla Lee. How suitable are the current design level verification tools for lesser known crypto primitives? I assume lesser known is anything other than encryption and signing, maybe?
Yeah, I mean, so she asked about the symbolic tools, is that right?
Design level formal tools.
Okay,
yeah,
gotcha.
I suppose symbolic.
Yeah, so at the design level, there's sort of like two camps. There's either symbolic tools, such as like ProVerif and Tamarin, which are better suited for verifying protocols. And then there's also tools like EasyCrypt, which are better suited to verifying primitives. And at least as far as I know, there shouldn't be any barriers when using like EasyCrypt to verify any primitive that you would want to verify.
Okay, good. We certainly have orders of magnitude more questions than can be answered live here. Looks like people are pretty interested in this topic, Kevin. So hopefully you and your co-authors can help answering these questions on Zulip afterwards. But thanks again for your talk and for answering all the questions. I think we'll move on though to the next talk in the session. Looks like it's the last talk of the day. This is a talk by Nadim Kobaisi on Verifpal, cryptographic protocol analysis for the real world. So Nadim, go ahead.
All right, one moment, please. Is this working?
Yes.
Thank you. Hello, everyone. It's a pleasure to be giving this talk at Real World Crypto. This is joint research between myself and George Onula and Mukesh Tiwari. This is Verifpal, cryptographic protocol analysis for the real world. So the preceding talk gave an excellent overview of the state of formal verification today. We have programming languages like F-star that tie an ML-like programming language with set3 theorem provers to get a state where types are proofs. And there we can produce functionally correct, side channel resistant primitives, such as the ones included in Hackle-N, and also fully functionally correct protocol implementations, such as the signal star implementation of the signal protocol. And then if we look at modeling protocols, we have tools such as Proverif and Tamarin and Cryptoverif that take models of protocols and then try to find contradictions to queries, or in the case of Cryptoverif, produce full game-based proofs. Because, you know, Tamarin and Proverif work in something called the symbolic model, and then Cryptoverif works in the computational model, and the computational model is indeed more detailed, allows for the production of proofs that can stand by themselves, right? Whereas the symbolic model, the proof is usually on the way that the tool works, and the tool produces analysis results. So we are going to be focusing on the symbolic model here because this talk and the whole point of this research is to focus on simple and intuitive formal analysis of protocols. And how simple can we go? How big of a compromise can we make in terms of soundness and completeness and still get results that actually mean something? So an overview of symbolic verification, you know, the big tools in the field right now are Proverif and Tamarin, and indeed they are being used more and more. In these tools, you write a model of the protocol. So if you're modeling Signal, you just model a key exchange between Alice and Bob. If you're doing TLS, you'd model a session between a server and a bunch of clients. And then you ask questions, essentially. Can someone impersonate the server? What happens if my phone is hacked and my keys are stolen temporarily, my state is hijacked temporarily? Do I get forward secrecy? And then Proverif and Tamarin try to find contradictions to these queries. So if you look at the paper that was discussed in the previous talk, the SOK, there was a list of these tools being compared, and the hope here is to add a new tool called Verifpal, and I hope to justify in this talk Verifpal's novelties or contributions to the domain. So I really believe in symbolic verification. If you look at the research, some of the research published recently, it's quite inspiring how you can have things like small subgroup attacks and invalid curve attacks on protocols that use Diffie-Hellman that are able to be modeled in the symbolic model quite expressively and in an interesting way that can catch new attacks. Also attacks on signature schemes and protocols that use signature schemes. Research by Cass Kremers, Dennis Jackson, Catriel Cohn-Gordon, and Ralph Sass is really showing that the symbolic model is far from boring. And also, you have many papers published in the past 4 years that are just analyzing signal, TLS, noise, protocol frameworks, scuttlebutt, Bluetooth, 5G, and so much more. So this is a great way to work. I really like the symbolic model because it's intuitive and it allows me to reason about protocols in a way that doesn't, the return on investment, I feel, is quite good. And so really the big elephant in the room, so why isn't it used more if it's so great? It's being used more a little bit these days, but why is the progress so slow? Well, so here is a quick example of Tamarin. And I have to admit, when I first designed the slide, I think I was being quite intellectually lazy. Here is also Proverif. And the naive thing to do here would be to just look at these languages and say, well, haha, they're so hard to learn and understand. Certainly we can do better. As it turns out, when you actually do due diligence and try to understand things properly, you realize that there is a good reason why these languages look like this, and that there is a level of expressiveness and sort of like the profundity of the analysis that you can actually get, and the profundity of the queries that you can ask does indeed benefit from this syntax. So the reason why Tamarin is like this, and the reason why Proverif is like this, there are very good, legitimate reasons that benefit from, in some cases, decades of research. And I want to make that very clear. I want to state that clearly. However, that being said, they still are hard to use. right? From the perspective of a student or a first year, perhaps student or an engineer. And so perhaps we can still try to cater to that space as well, while respecting that these design decisions were not perhaps as misled as one might believe at the beginning. So Verifpal is new protocol analysis software. It has 4 main goals. And one, an intuitive language for modeling protocols. 2, modeling that avoids user error. 3, analysis output that's easy to understand. And 4, it essentially tries to combine itself with the surrounding ecosystem, integration into Visual Studio Code, translations into ProVerif and Calc and other stuff. These are the 4 main goals that I just discussed. You can see here on the left. They provide a user-focused approach. However, hopefully without losing too much strength. We can still reason about advanced protocols such as Signal or DP3T out of the box. We can analyze for post-compromise security and so on out of the box. We can model for fresh values and unbounded sessions and other cool symbolic model features. I need to specify, I think ProVerif probably has a better grasp of unbounded sessions than we do at the moment, but we are targeting these goals. And so really, this is not something that produces full game-based proofs like Cryptoverif. ProVerif doesn't either. But also, it is not formally proven to not miss attacks the way that ProVerif is. Our work on formalizing Verifpal and Calc really is pushing us towards getting more and more formalization on the soundness of the analysis logic, but we are not quite there yet. We are working on obtaining this higher confidence, but we are conscious of the trade-offs that we're making to get this simple language and this analysis that allows you to really prototype and draft and like whiteboard protocols and immediately get feedback with little investment into what you're trying to say. And I think this allows a lot of creativity and a lot of learning and a lot of understanding to happen with students and engineers that I think is truly valuable. So long as you understand and are just sort of intellectually honest with what you're doing and the trade-offs and the responsibility and so on. So here, if you look on the left, you'll see an example of a simple protocol modeled using Verifpal. And I really like how you can just say, Alice is sending a message to Bob, and Bob is doing this, and he's generating B, and Diffie-Hellman looks very intuitive, right? And we can capture all of this and also give an intuitive experience. And as you may recall, the second priority was eliminating user error. So in Verifpal, you can't define new primitives. And that's not because of anything other than we don't want users to define new primitives. We ship with hashing primitives, MAC, HKDF, password hashing such as script, encryption, authenticated encryption, public key encryption, signings, ring signatures, blind signatures, Shamir secret sharing, and so on. And so we want to give you primitives. We know we've specified them according to a universal specification built into Verifpal that is called primitive spec that is used to model any primitive. And then we know that you're basically going to be able to understand what to expect from these primitives. And we're not targeting users that want more. If you want to specify your own primitive, ProVerif and Tamarin really do provide, you shouldn't be using Verifpal. You should be using tools that are more advanced, really. And so Verifpal's syntax is also fairly expressive. For example, if you add little brackets around a value as it's being sent on the network, as you can see here in orange, you'll see that this becomes a guarded constant. And so it's basically not mutatable by the active attacker. And this can be used, for example, to model pre-shared keys. And also, if you add a little question mark, this makes it such that a primitive is a checked primitive. So if signature verification fails, the client here will abort their execution of this particular execution of the protocol in which its signature verification fails. This is a giant thing that I shouldn't have included, but basically there is a sort of formalism as to how Verifpal works. Here's the primitive spec on the left. I should use my time to talk about things that are more relevant since I only have 10 minutes. So we have advanced features. We have protocol phases that allow for temporal logic, and this allows you to model things that happen in different periods of time. And this is necessary for modeling for forward secrecy, post-compromise security. You can also leak values to an attacker. Recently, we introduced unlinkability queries and freshness queries, and these are quite important for modeling something like the DP3T contact tracing protocol. And we also have password values that are crackable unless you first hash them. I thought this was a fairly unique feature. Turns out ProVerif has a similar feature. And also query preconditions, which allow you to basically relate queries together. And of course, this is a feature that this is a very common feature. And so We also have Verifpal for Visual Studio Code. It's a shame I can't talk more about this because it's really good. You know, like the integration into Visual Studio Code, you can run Verifpal analysis from inside Visual Studio Code, generate graphs, format your models, upload them to Verifhub. Oh, we have a thing called Verifhub. I don't have a slide on it, but there's like this, like GitHub for Verifpal models, and you can upload your Verifpal model there and share it more easily. The translation to Coq and ProVerif is really good. It forced us to basically have a better understanding of the formal semantics and have lemmas and proofs on how everything works. And also we're translating Verifpal models automatically to ProVerif models. Both of these things need more work. This stuff is really hard, but it works kind of, and we're getting it better. It's under active development with my co-authors. The analysis output is easier to read. Here on the left, you can see what ProVerif analysis output looks like. On the right, there's a Verifpal attack trace. And the Verifpal attack trace is colored also if you look at the terminal output, which I'm sure is very important. There you go. There's one. We've analyzed Signal, Scuttlebutt, Proton Mail, Telegram, DP3T using Verifpal. And we haven't found new attacks, but every time the analysis has matched what we've expected, and also other formal analyses using similar tools in the field. People are using Verifpal. So Asa Abloy makes locks and smart locks. They've used Verifpal. I know some engineers at Google have used Verifpal, but they just like sent bug fixes on the mailing list. I don't know if usage as Google is more important than that. It most likely is not. Quarks Lab uses Verifpal a lot. Zoom has used Verifpal in order to like just early sketching and prototyping of the Zoom, of ideas for the Zoom protocol. But it also led to finding an early flaw in one of those prototypes. And I'm very proud of that. I think Verifpal, so what's really interesting to keep in mind is that the Zoom team, you know, like they could have invested a lot of time in learning, for example, ProVerif and Tamarin, getting better results, more sort of elaborate and profound results. But is that really a priority for an engineering team early in the design phase? I don't think it even should be, really. I think in the early design phase, you want to quickly sketch and whiteboard and get meaningful feedback, but with little investment. And Verifpal is excellent at that. I'm really proud of that it was able to be used in these contexts. The Verifpal user manual also means that Verifpal has been a huge success in teaching. So I taught a class at NYU, and Verifpal was able to actually get 20-year-old undergraduate students with no background whatsoever in security. These are first-year, second-year students, and they're modeling protocols and understanding security goals. I also think this is a great success. And so now we're working on something called Verifpal Heroes, which is going to be a very long and elaborate, hopefully, illustrated guide to protocol verification. And it uses Verifpal as an introduction into the field, but then from there it goes into ProVerif and Tamarin and CryptoVerif and EasyCrypt and F-star and Coq. And as you can see, we're sort of expanding the sort of almost ridiculously approachable sort of like style that Verifpal has with the sort of illustrations and so on to cover all of these tools, because we really want to focus on pedagogy as well as being something that is useful and sort of makes sense for engineers and students.
Nadim, good. I was just going to interrupt it.
To conclude, my co-authors, Giorgio Ula and Mukesh Tiwari, I believe are at this conference. Giorgio is just finishing his undergraduate, is going to start his master's. He has done incredible work for an undergraduate student. He worked so much on the Coq aspect, on formal semantics of Verifpal. I strongly encourage you to hire Giorgio. He really deserves it. I'm so grateful for the way Giorgio and Mukesh have been able to help me out and contribute to this project. So I just wanted to shout out. That's it. Thank you so much.
Great. Thank you, Nadim, for that exciting talk. We have a couple of questions on Zulip. The first question I'll take is from Nigel Smart. You listed secret sharing very quickly, and it looked like it might have just been 1 out of 3, Shamir. Do you allow arbitrary threshold secret sharing? And also, do you model the fact that secret sharing is linear? Like that's a common property used in MPC protocols, for example.
So for the first question, we do not allow for more than 3. And this is for no good reason. We could allow it. I guess I haven't worked that in yet. We could easily expand that. For the second thing, I don't think that really can be captured. I might be wrong, but as far as I understand, I don't think that can be captured in the symbolic model.
Okay, well, there was an aside in Nigel's question, which I didn't read, but he said, similar to how you model Diffie-Hellman, you have a group operation. So there's some algebraic reasoning, presumably, in the model.
Well, the way that you model something like Diffie-Hellman, so tools like Tamarin have a more profound understanding of Diffie-Hellman, but in Verifpal, it's just a equation where you basically say, and in some sort of basic Proverif models, g to the b to the a is equal to g to the a to the b. And you're basically just satisfied with that. And you could expand that, but so far, this is what we've stuck with.
Great. A question from Jonathan Hoyland. What is the performance of Verifpal on massive protocols like TLS? Do you have to split it into pieces, or can you analyze it monolithically?
Oh, man. So right before Real World Crypto, we did so much work on improving performance. It's written in Go, and so we're able to use multi-threading, and we're kind of improving also the inner, we did a lot of graphing of the performance. Something like TLS takes a very long time. Even something like Signal takes a long time. But at the same time, I recall that when I modeled IKPSK2 in Proverif, and this was with also assistance from people who were very expert in Proverif and giving me pointers on how to make the model go faster, it still took 30 days to get the result. It took 30 days to get that result in Proverif. And it was in the winter, which is great because I had free heating in my house. And that was quite excellent, really. But Tamarin also can take a very long time on certain protocols. And this is just a thing that we have to deal with. But we are working on making it fast. And I think currently it is reasonably fast.
Okay, I think I'll pass along one last question. Thanks everyone for staying a few minutes late. A question from Sebastian Verschoor. Given that Verifpal might miss attacks, are you not afraid that protocol designers might mistake the output for a proof of security?
You can miss attacks so easily by modeling the protocol. So I have looked at many protocols written using tools that are decades old, that have been under development for a long time. And attacks are very frequently missed just because the model is not comprehensive enough. And it's quite difficult to have a comprehensive model when you're working in the symbolic model and even in the computational model, because you're always restricting yourself to a sort of elegant representation model, really, of the protocol. We are, I think, very clear about Verifpal's capabilities. And I think that, especially in the last little while, it has become quite adept at finding the attacks that one could reasonably expect it to find, and a lot of times attacks that are a bit surprising and unexpected. None of this stuff is perfect. And I think that ultimately, whether even you're using something that is really, truly quite impressive, an impressive feat of theory and engineering like F-star, you still find bugs in F-star that are quite simple sometimes.
Great. Well, on behalf of all the audience members, I just want to thank Nadim and Kevin for their really interesting talks. There's lots of questions for both sets of authors on Zoom. I hope you'll have a chance to look through those.